Hello, I'm Professor von Schmohawk, and welcome to YU. In the previous lecture, we saw that any number with an exponent 1 over n represents the nth root of that number. In this lecture, we will show that exponents can also be fractions with numerators other than 1. In fact, an exponent can be any positive or negative rational number. To illustrate how this works, let's start with the cube root of a, which can be written as a to the 1/3 power, and then square it. As we saw in the chapter on raising exponential expressions to powers, we can simplify the expression on the right by multiplying the exponents 1/3 and 2, which gives us a to the 2/3. So a to the 2/3 represents the cube root of a squared. However, we could have also come up with a to the 2/3 in a different way. Instead of squaring the cube root of a, we could have first squared a, and then taken the cube root. Using exponents, this would be written as a squared to the 1/3 power, and multiplying the exponents, once again we get a to the 2/3 power. So in both cases, we get a to the 2/3 power, regardless of whether we start by taking the cube root of a and then squaring it, or start by first squaring a and then taking the cube root. It may seem strange that both these operations give the same result. However, if we pick a value for a which comes out even, it is easier to see why this is true. For example, let's say that a is equal to 8. Now on the left side, the cube root of 8 is 2, and 2 squared is 4. While on the right side, 8 squared is 64, and the cube root of 64 is also 4. If this still seems a bit like magic, let's look at it another way. Let's start by writing the number 8 as 2 times 2 times 2. When we take the cube root, this leaves us with 1 2. Then squaring this gives us 2 2's. On the right side, we again start by writing 8 as 2 times 2 times 2. We then square this quantity, giving us 6 2's. Then, taking the cube root leaves us with 2 2's. So in both cases, we end up with 2 2's multiplied together, which equals 4. It is now easier to see why both operations produce the same result. On the left side, we first eliminate all but 1/3 of the factors, and then multiply the number of factors by 2. While on the right side, we first multiply the number of factors by 2, and then take 1/3 of the factors. Since it doesn't matter in which order we multiply the number of factors by 1/3 and 2, either way we will end up with the same number of factors, and we'll get the same result. So we have two options for evaluating an expression with a fractional exponent. We can raise the base to a power specified by the numerator, and then take the root specified by the denominator. Or the operations can be performed in the opposite order, taking the root first and then raising the result to a power. Either way, we get the same answer. However, the amount of work that we have to do can be a lot different. Let's do this example both ways and see why. If we square 27 first, we get 729. Then taking the cube root of 729 gives us 9. On the other hand, if we take the cube root first, we get 3. And squaring 3 gives us 9. Either way, we get 9. However, the second way is a lot easier. In the beginning of the lecture, we said that an exponent can be any rational number, and in general, we can write this as the integers m divided by n. But what would a negative rational exponent mean? If we take a non-zero number, a raised to the 0 power, and divide it by the same number with a rational exponent m over n, we subtract the exponents, so the result will have an exponent of negative m over n. Since a to the 0 power is equal to 1, this tells us that any number with a negative rational exponent is equivalent to 1 over that number with the same positive rational exponent. Rational exponents follow all the same rules we already know for integer exponents. For example, in an expression written as a fraction, we can move the exponential terms from the denominator to the numerator, or from the numerator to the denominator, as long as we switch the sign of its exponent. As an example, let's say that we want to write an expression 1 over the square root of x without using a radical sign. We can eliminate the radical sign by writing the square root of x as x to the 1/2 power. But then we can simplify this expression further by moving the x term from the denominator to the numerator and switching the sign of the exponent. So 1 over the square root of x can be written as x to the negative 1/2 power. Radical expressions can often be simplified by using the rules of exponents. For instance, let's simplify the expression a over the square root of a. We start by writing the square root of a as a to the 1/2. If we write the a in the numerator as a with an exponent of 1, we can subtract the exponents, giving us a to the 1/2, or the square root of a. So a over the square root of a can be more simply written as the square root of a. As another example, let's simplify the square root of a over the cube root of a. We start by writing the square root of a as a to the 1/2 and the cube root of a as a to the 1/3. We can then subtract the exponents 1/2 and 1/3. Using a common denominator of 6, we write this as 3/6 minus 2/6, which gives us a to the 1/6, or the 6th root of a. So the square root of a over the cube root of a can be more simply written as the 6th root of a. Let's do one more example, simplifying the cube root of a squared over the 6th root of a. We can start by writing the cube root of a squared as a to the 2/3 and the 6th root of a as a to the 1/6. We then subtract the exponents 2/3 and 1/6. Using the common denominator 6, we can write this as 4/6 minus 1/6, which is 3/6, or 1/2. Of course, a to the 1/2 is the square root of a. So the cube root of a squared over the 6th root of a can be simply written as the square root of a. So we have seen that roots can be written as exponential expressions using rational exponents, or as radical expressions using a radical sign. We have also seen that these expressions can be simply written as an integer if they are perfect roots. In the next lecture, we will see that these expressions can sometimes be simplified even when they are not perfect roots.